Alright, so this is the second attempt. My brain is really bad today. So I'm going to try to get through this without making too many mistakes. Just kind of bear with me. It's less about going through this problem again and more about showing you how you can use Wolfram Alpha. But because this was a nasty, complicated problem, then I want to take you through it to show you how you can utilize Wolfram Alpha and then make yours match theirs if it doesn't already. So here we go. You can hear the dog in the background. I've been up since 3. It's now after 6. Anyway, so what we want to do is we want to take ddx of this stuff. So sine pi x plus cosine pi y. And we want to square that. Now I'm putting the brackets here because it's a little bit easier to see. Remember that this is an inside, so we're using the chain rule here. I'm going to call this u. So that means that du dx is going to be equal to the derivative of sine pi of x, which is the derivative of sine, which is cosine, times the derivative of what's inside. Remember, this is all in accordance to x, so we're still straight. We just take the derivative of the inside, which is pi. Bring that out. Plus. And if you want to jump to the minus, go right ahead. Alright, so now we have a bigger issue here. We've got cosine, but we also have y, which is a function of x itself. So we've got a double issue of implicit differentiation here. The derivative of cosine is going to be negative sine, and that's going to have that stuff inside. And then we need to take the derivative of what's inside. And so if I just kind of pull this stuff out here, I'm going to call it w. W is equal to pi y, which is a function of x. Then dw dx is equal to, and this is, the pi comes out as a multiplier, and then we just have whatever the derivative of y of x is, which is just y prime. So that's the multiplier then that comes out and sits back here. This is pi y prime. Keep in mind, this is multiplying the negative through. So if I rewrite this, just so it's a little bit more clear, I'm going to have pi cosine pi x, not pi of x, minus, and then this is going to be pi y prime of sine of pi y. Okay. So now we go back to our original level. I know, right? This is horrible. But anyway, we go back to our original level, and we're saying, all right, well, we want d dx of u squared now. But u is a function of x. And so I'm going to need to take the derivative of the outside, which is just 2u, and times the derivative of the inside, which is u prime, or if you feel better about it, it's du dx, because that's what matches here. So when we plug all that stuff in, we're going to get 2 times all of that junk. So sine pi x cosine pi y, plus, let's put the plus in there, and then multiply it by this junk here. So multiplied by pi cosine pi x minus pi y prime times sine of pi y. There we go. All right. So hopefully I can keep my head about me when I go to do this. All right. We took the derivative as we did yesterday. I'm not going to expand it. We tried to expand it yesterday. Did not go well. Did not give us any more insight. And so there's really no purpose in it. So now I'm going to try to keep this up where I can see it. I'm going to drag this over so I can see both things. So I've got my Wolfram Alpha here, and I need to move this over so that I can see my solution here, and we're going to see if they match up. So whenever you're putting in a derivative into Wolfram Alpha, you're going to want to put in d over dx to start, and then you're going to open up a set of parentheses. In that set of parentheses, you are going to put whatever your function is. So, like I have sine all of this junk squared, I need to put parentheses around all that crap. So you notice I have an outer set of parentheses here. And you'll notice that it highlights in green just for a little bit to show you that these are the sets that open and close. You want to make sure that that is completely surrounding your function. Once you do that, going through and putting in your function is a fairly standard practice. It does have a math input kind of thing, so if you're not exactly sure how to do it and you just kind of want to throw it in there in a more natural sense, then you can put in math input and it will guide you through the entire process. So, for instance, I don't really want to do it here because it's long and drawn out. But you're going to put it in just like you see it. The only difference here is going to be when you see pi, just spell it out, pi, and then put an asterisk, which is shift 8 for multiplies. And it's very, very, very important here. You have to put y and then parentheses x and parentheses so that you say y of x. If you don't, then Wolfram Alpha will assume that you are talking about x and y as being independent variables. And I'll show you what happens. If you end up not putting that in, it'll spit back this little curly Q deal, which is known as a partial derivative. It's assuming that you have a function z equals something of x and y, and you get a three-dimensional object. That's not what you're going for. But you have to put this parentheses x at the end of the y to force Wolfram Alpha to look at it as a single dimensional or single variable equation. All right. So we got all of that. So now we come down here and we notice immediately we have a 2 pi out in front. Don't freak out. Because what we notice in here is in this other factor, we have a pi out front in both. We can factor that out as 2 pi times that stuff, which is that sine pi x plus cosine pi y. And then the pi's have been drawn out, so this is cosine pi x minus y prime sine pi y. All right, now we start taking a look at it and we notice, remember our y of x is just y. That's what it is for us. So we have 2 pi. And then in parentheses, we've got this cosine pi y, which we have, plus sine pi x. Now, why they put it in that order, I don't know. Something in the coding. But I think they just prefer cosines first over sines. And then we have cosine pi x, which is this, minus y prime. Again, ignore that of x and just call it y prime. Sine of pi y, which is pi y of x. And so we match what they've done. And this is called the computer algebra system. It's really cool. So if you want to check every single problem you do on it, just again, make sure that you're going through and you're putting y of x. So even if I wanted to do the first one here, which is just x squared plus y squared equals 36. And I'll use that one to show you the math input. So if I want to go to math input, I just go d, and then I call my variable, and they guide you through this process. So d dx, and then I need my function here. And so this is going to be, and because it has the box, you don't technically need parentheses. But you have x squared, not 23rd, and then plus y squared. And then the equals 36, you kind of have to just understand you separate it by yourself. And now remember, we have to go back to this y and say y of x. And then we'll just let it run and see what happens. And so it says you have 2 times y of x times the derivative of y of x. So it's 2y y prime, which is the implicit part of our derivative here. And then the derivative of x squared is just 2x. Now, because of that, because you have 2x and then 2yy prime, it factored out the 2 automatically. That's why you have this 2 out in front. So if you go through it, you're going to have 2yy prime plus 2x, which is this in a different form. So it's just kind of a cool system to double check all of the stuff that you're working on. Okay. I'll try to make a little thing here to say skip to this point. It's already 10 minutes and it's just a hot mess. So I'm going to go ahead and jump to something from 21 to 28. And now we've talked about these, so I'm going to just do another one because we did number 32 in class. Let me take number 24. Now, number 24 says I have x plus y cubed equals x cubed plus y cubed. If you wanted to, you could go through and say, all right, well, expand this out and you'd have an x cubed and a y cubed. If you want to go through that process, go for it. I'm not going to be all that excited to go through that process. So on both sides, I'm taking dy dx. X plus y quantity cubed equals dy dx of x cubed plus y cubed. First derivative here. It's the derivative of the outside, which is 3x plus y squared, times the derivative of what's inside, but it's 1 plus y prime. So that's the first half. The second half, oh my gosh, puppy dog, you're snoring. Poor puppy dog's been up with me the whole time. But anyway, we take the derivative of this stuff over here, which is a little bit easier, so we say equals. And then the derivative of x cubed is just 3x squared. The derivative of y cubed, again, remember the implicit, is 3y squared times y prime. All right, now our goal is to get with the y primes together. This is where you could have expanded this using the binomial theorem and then gone through, did some subtractions, and you'd end up with a slightly cleaner, and I use that in quotes, a slightly cleaner equation. So if I expand this out, I'm going to get 3x squared plus xy times 2 is 2xy times 3 is 6xy. And then I have 3y squared. And I've got this stuff here. 1 plus y prime equals, and then this is 3x squared plus 3y squared, y prime. Remember, my goal is to get my y primes together. That's my goal. So I'm going to make a hot mess of this stuff here. So using distribution, this is going to be, this stuff times 1 is just going to be 3x squared plus 6xy plus 3y squared. And then times that stuff. And so I'm going to go plus y prime times this stuff, which is 3x squared plus 6xy plus 3y squared. Okay, equals 3x squared plus 3y squared y prime. What I really want to do is I really want to get this term and I really want to get this term together. So I'm going to subtract 3x squared from both sides. When I do that, these two cancel out. They'll eliminate one another. And now I've got, oh, come on now. Let's behave. 6xy plus 3y squared. And I'm moving this one over. So this is going to be equals 3y squared y prime plus y prime. And I want you to get used to this. 3x squared plus 6xy plus 3y squared. So the reason I want you to get used to this is you notice you have two factors that are the same. So that gets pulled out. And then what's left gets added. So it's 3y squared plus 3x squared plus 6xy plus 3y squared. Now what we can do is we can go through And we can divide both sides by that so that we get 6xy plus 3y squared over 3x squared plus 6xy. 3y squared and 3y squared is plus 6y squared. And for the sake of calculation, I am going to do what we did yesterday. I believe Sam suggested it. We're going to divide everything by 3, so we can cancel this out, become a 2. That cancels, this becomes a 2, this becomes a 2. It just makes things a little bit easier to calculate. And so this is going to be 2xy plus y squared over, and this would be x squared plus 2xy plus 2y squared. Now, you can stop here, and that's perfectly fine. I got to go to the point negative 1, 1 for the point negative 1, 1. This is not too bad of a number. If this was any worse of a number, then what I would do is I would actually break this up. If you do that, you notice that you have an x squared plus 2xy plus y squared plus y squared. This here is x plus y quantity squared plus y squared. If we were to do that, it actually breaks it down pretty easy. X is negative 1, y is positive 1. This goes to 0. And so I just have this in the bottom. So really now I have 2 times negative 1 times 1 plus 1 squared all over 1 squared. And now this is going to give me what? Negative 2 plus 1 is negative 1, or yeah, it's negative 1 over 1 is just negative 1. And that's the answer. So there's lots of, it's not the calculus so much, although implicit is pretty freaking nasty. It's not the calculus so much, it's the algebra. And being able to recognize stuff like this, where you can change it out a little bit, that is, it's not even important. It's almost vital, because sometimes you just can't do anything except that to really simplify stuff down. So I want to encourage you to think deeper into the problem and see if you can come up with this little stuff that you might have forgotten. And in order to do it, it takes practice. It really does. So if you want to stop up here in the violet or periwinkle or whatever color that is, if you want to stop there, that's perfectly fine. You can do it. It's just going to be a lot more raw calculation. But I encourage you to look a little bit further beyond that. Try to recognize some of these cool factorings, and you notice it just goes to 0. So like 3/4 of your problem disappears, and that's kind of nice about that. I know calculators, you guys don't think about it because they just plug it in, but that's a lot of plug in. I mean, I can make so many mistakes in plugging that in, so I don't trust myself, but that's a me thing. All right, I hope this helps you guys in the implicit. I will be back tomorrow, even if I'm on my deathbed. I despise taking days off. So, all right, I will talk to you guys tomorrow. If you have any questions, throw me an email, and then we're going to be starting to close out this unit. And so I'm looking by the end of next week to have a test over basic differentiation. There's only one more topic I want to hit before we move on, and that is going back to limits and talking about L'Hopital's rule, how it works, and how to use it. And that's what we're going to do tomorrow. So Monday we'll start review, and we'll start working on AP problems, and then I'm going to have a full review on Wednesday, Thursday, and Friday test. All right, y'all. Behave. Be good. Talk to you soon.